Hello everyone. In this video I am going to discuss on a very important topic in linear algebra, the Gram-Schmidt orthogonalization process. The main object of this paper is to find out an orthogonal and hence an orthonormal basis of a finite dimensional inner product space from any given basis. Now here is the statement. Every non-null subspace of a finite dimensional inner product space possesses an orthonormal basis. Now come to the proof. Okay. Suppose V is a finite dimensional inner product space over a field F and W be a subspace of it. Since W is finite dimensional, it must have a finite basis with the vectors say alpha 1, alpha 2 up to alpha r. Okay, we know that the basis vectors are always non-null vectors. Basis vectors are always non-null vectors. So all of these vectors are non-null vectors. We are going to construct orthogonal vectors from these vectors alpha 1, alpha 2, alpha r. First we have to pick up any one of these vectors and rename it by beta 1. Without loss of generality, we take the first vector alpha 1 as beta 1. We take the first vector alpha 1 as beta 1, that is beta 1 is equal to alpha 1. We now construct the second orthogonal vector beta 2 using alpha 2 and previously made beta 1. How? Beta 2 is alpha 2 minus c1 beta 1, where c1 is the scalar component of alpha 2 along beta 1, that is c1 is equal to inner product alpha 2 beta 1 upon inner product beta 1 beta 1. Okay, then obviously beta 2 is orthogonal to beta 1 because here it is inner product beta 2 beta 1, this is equal to inner product alpha 2 minus c1 beta 1 comma beta 1. After little bit of calculation we get this is equal to 0, that means beta 2 is orthogonal to beta 1. This is here beta 2 is orthogonal to beta 1. Okay, and we have linear span of beta 1 beta 2 is same as linear span of beta 1 alpha 2 is same as linear span of alpha 2 alpha 1. Okay, I am going to see this. Okay, linear span of beta 1 beta 2 is same as linear span of alpha 1 alpha 2. Suppose gamma is a member of linear span of beta 1 beta 2, then gamma can be written as some scalar into beta 1 plus another scalar p2 into beta 2. This is beta 1, this is beta 1, and for beta 1 I can write alpha 1. So this is p1 minus p2 into c1 alpha 1 plus p2 into alpha 2, some scalar into alpha 1 plus another scalar into alpha 2 belongs to linear span of alpha 1 alpha 2. So we took a member from linear span of beta 1 beta 2 and get it in linear span of alpha 1 alpha 2. So linear span of beta 1 beta 2 is a subset of linear span of alpha 1 alpha 2. In the same process we consider an element from linear span of alpha 1 alpha 2, and after a little bit of calculation we get it in linear span of beta 1 beta 2. That means linear span of alpha 1 alpha 2 is a subset of linear span of beta 1 beta 2. From this and this we get linear span of beta 1 beta 2 is same as linear span of alpha 1 alpha 2. Okay, now another claim is alpha 3 cannot be in linear span of alpha 1 alpha 2, because if alpha 3 is in the linear span of alpha 1 alpha 2, then we have already got that alpha 1, alpha 2, alpha r are linearly independent vector, and so alpha 1, alpha 2 and alpha 3 are also linearly independent. So we have arrived at a contradiction to the fact that alpha 1, alpha 2, alpha 3 are linearly independent. So we must have alpha 3 is not in linear span of beta 1, beta 2. Okay. Okay, we now construct the third orthogonal vector beta 3 using alpha 3 and previously constructed beta 1 and beta 2. How is it? Beta 3 is equal to alpha 3 minus d1 beta 1 minus d2 beta 2, where d1 is the scalar component of alpha 3 along beta 1 and d2 is the scalar component of alpha 3 along beta 2. Then we can show that beta 3 must be orthogonal to both beta 1 and beta 2. Okay, here is a little calculation. Inner product beta 3 and beta 1, write the value of beta 3 as alpha 3 minus d1 beta 1 minus d2 beta 2, inner product with beta 1. Okay, next write down the value of beta 2 in terms of alpha 2 and beta 1, that is beta 2 is alpha 2 minus c1 beta 1 with inner product beta 1. So after a little bit of calculation I get this. Now inner product beta 1 with beta 1 is cancelled out. Here this beta 1 cancelled out. We finally get inner product alpha 3 beta 1 minus inner product alpha 3 beta 1 minus d2 into inner product alpha 2 beta 1 plus d2 into inner product alpha 2 beta 1, finally giving you 0. That means beta 3 is orthogonal to beta 1. Similarly we can show that beta 3 is orthogonal to beta 2. Okay. Also, as in the previous, linear span of beta 1, beta 2, beta 3 is same as linear span of beta 1, beta 2, alpha 3, which is same as linear span of alpha 1, alpha 2, alpha 3. Now we have r vectors in our given basis. So this process of making the new orthogonal vectors must terminate after a finite number of steps, because at each step one alpha I is replaced by one beta I, such that the new set becomes orthogonal. So in the final step we obtain beta r is equal to alpha r, and with the help of previously made beta 1, beta 2, beta r minus 1 as beta r equal to alpha r minus b1 beta 1 minus some b2 into beta 2 minus so on br minus 1 beta r minus 1, where b1 is the scalar component of alpha r along beta 1, b2 is the scalar component of alpha r along beta 2, and in the same way br minus 1 is the scalar component of alpha r along beta r minus 1. Here it is. Clearly beta r is orthogonal to each of the vectors beta 1, beta 2, beta r minus 1, and also as previous we have linear span of beta 1, beta 2, beta r is same as the linear span of alpha 1, alpha 2, alpha r. Therefore beta 1, beta 2, beta r is an orthogonal basis of the subspace W, and with the help of these vectors we can find out the corresponding orthonormal basis as beta 1 upon norm beta 1, comma beta 2 upon norm beta 2, and so on beta r upon norm beta r. That's all.